Hi, I'm Kathy Resnicek.
I'm Richard Pressler.
And we're here today to introduce you to the K-12 Wired Networking course offered by TAPT. So hi Richard, thank you for being here today.
Oh, you're welcome.
Can you tell us first a little bit about what you do with wired networking, and especially in the context of K-12 education?
Sure. So I work in the private sector. The company I work for is called All Connected. I'm the Chief Technology Officer. But we have a lot of customers that are in the K-12 sector. And essentially what we do is we design and implement and in some cases operate their computer networks. We do deal with both the wired network, the wireless network, as well as other parts of the infrastructure. But for this course, we're really focused in on wired networking. And so we're in a support role, oftentimes supporting the IT departments within K-12 school districts. And then other times we're simply there for a project to implement a new network.
Yeah, and I know that you've helped VCOE out a bit, so thank
Happy
you
to.
very much. Let's talk about the range of learners for this course. Who is this course meant for?
So it's really meant for somebody who's been kind of pushed into the IT network admin role. Maybe it was their choice or not, but that can happen, right?
Yes, definitely.
But they may have been an educator, perhaps, and then they were asked to take control of the computer network. And so this course is really designed to kind of give them that fundamental information and then build on it. I would say by the end of the course, though, they would be a quite proficient network administrator. So even if someone comes in with a good amount of knowledge, there's material that's basic that they can skip over and look for the more advanced things, and they should be able to glean something from it.
Great, so it's kind of meant for a wide range of learners.
Yes, it could address a wide range.
Great. So can you describe a typical K-12 wired network? Is there such a thing as a typical K-12 wired network?
There's a few things that make K-12 networks unique. You know, as far as the actual equipment used, it's pretty much the same. Whether you're in a school district or you're in a commercial entity or an enterprise, often the equipment ends up being very, very similar. It's not like manufacturers, for the most part, have sought out to make a switch or a router that's just for K-12, you know. So a lot of this knowledge and information is shared across many, many different industries. But we do have some interesting challenges. For example, in recent years, there's been a lot of initiatives to assign one device per student. Well, what that does is it increases the load on the wireless network. So now there's more wireless access points. Now those access points have to be powered and they have to have network connectivity. So the wired network has to expand to support really the wireless network.
That makes sense.
Same things with smart TVs or these smart boards, things like that. A lot of them are connected to the wired network in order to communicate across the LAN. And in order for that connection to happen, well, again, we have more cabling, we have more switches, we have more requirements. So K-12 has a density that is somewhat unique. In the commercial space, we usually don't achieve those levels of density.
That makes a lot of sense. And so having a good, strong wired network supports the learning that we want to have happen in schools, as well as the business of schools.
Yeah,
right?
really, it supports everything. I mean, and even aspects of redundancy and resiliency, which we're going to address in this course, are necessary now. At one point in time, if the computer network was down in a school district, people would switch to other methods. They could use paper, they could even take attendance on paper, things like that. Some of those methods are still available, but boy, nobody wants to use them anymore. I mean, it's just so tedious. So the computer network being down or unavailable is really not acceptable anymore in a modern K-12 environment.
I've been in the office when the power goes out and everybody goes, can't work.
Right, yeah. And now it's can't teach, right?
That's right, can't teach.
Yeah, can't teach.
Awesome. So you mentioned resiliency and redundancy and stuff. So let's go through kind of some of the things that are going to be addressed. So give us a little snippet of each of the modules in the course, please.
Sure. So the first module is all about fundamentals. So I like to describe this as the module about things you can see and touch. So it's the cables, the equipment, the rooms the equipment go in, all of those things. And then towards the end of the module, we're going to start talking about the theoretical, how to think about a computer network in terms of its layers and things like that. And that sets the tone for Module 2. In Module 2, we really get into what is a LAN and what is a WAN, and how do you understand and operate the protocols on a LAN or a WAN. So we're going to talk about layer 2 protocols, we're going to talk about layer 3 protocols, and those are layers from that reference that I mentioned in Module 1. It's called an OSI model, but it's essentially a theoretical model of computer networking. In Module 3, we're going to talk about quality of service. I feel that this is an important topic to consider. I think it's one that's overlooked quite often. Sometimes people will feel that they'll just have to go to the next speed. They'll have to increase from 1 gig to 10 gigs or from 10 gigs to 40 gigs because of a network quality issue.
Okay.
But there's a lot of ways to address quality, and it really comes down to prioritization of data based upon the business needs. And so we're going to talk about that a lot in Module 3. Module 4, we're going to get into security. That's a
hot topic.
Well, it's not only a hot topic, but for me, for the infrastructure person, it's bigger than a module. It's bigger than even a whole, there's a whole course.
Well, we do have a course on cybersecurity, so that will be helpful. But so you'll introduce a little bit of that, right?
Well, and what I'm focused on in this module is really the best practices for the equipment that's being installed.
Okay.
So, for example, when you install a new switch, how do you secure that switch so that nobody can access it that's not authorized, right? Because they could cause a lot of damage if they get into your equipment and they start reconfiguring it. There can be a lot of problems. So we're going to talk about very low-level security stuff. We are going to talk about firewalls a little bit. Yes, a little bit. But we're not going to get into this whole next-generation firewall concept and some of the more advanced things. And then in Module 5, we're going to focus on troubleshooting. So we're going to focus on some tools that you can use, like Wireshark, in order to analyze packets and understand what's really going on within the computer network.
And so you're going to show some tools, but are those tools expensive? Or?
No. We're focused on things that are either open source or freely available. Like
great.
Wireshark, you can just go download it. Learning to use it takes some time and some effort. So we're going to cover some of that in Module 5, how to use it to troubleshoot. It is a pretty deep tool, but it's worth understanding, and so we'll focus on that.
That all sounds really great. I'm looking forward to exploring all the modules in this course. So we'll see you in Module 1.
See you.
Welcome back. I'm Kathy Resnichek with the Ventura County Office of Education.
And I'm Richard Pressler with All Connected.
And we're here to introduce the first module in the wired networking course, Networking Fundamentals. So Richard, can you give us an overview of what people are going to experience in this first module?
Sure. So most of this module is focused on the things you can actually see. So you can see a switch, you can see a router, you can see a hub, you can see the cables in the wall. It's focused on that. And then it's also a little bit about the theoretical understanding of how a computer network operates. So it's broken up into 4 assignments. The first one focuses on cabling. So we'll talk about how cables are used to transmit digital.
Sounds exciting.
Yeah, I'm glad you're excited about it. That's good. The next one will be the network equipment. So the hubs, the routers, the switches, things like that. And then we'll focus on the rooms that the equipment goes in.
That's probably really important.
It is, and we've run into a lot of issues over the years with the various rooms that these very expensive pieces of equipment are placed in.
Looking forward to some good stories on that one.
So it's worth an assignment. And then finally we'll talk about that theoretical model, the OSI model. It's just a way of understanding computer networks in a layered fashion. Because they really are layered one thing on top of the other. You can use a variety of different kinds of cables, variety of different kinds of switches, different manufacturers, and there's a reason why that interoperability exists. So we'll dig into that a little bit.
That sounds great. So for every assignment, you're going to be adding to your G portfolio. And you're going to be talking about all these things that you're learning about within the context of your own K-12 network.
Excellent.
Welcome back. I'm Kathy Resnichek.
I'm Richard Pressler.
And we're going to be talking about the first assignment in the Network Fundamentals module. So can you give us a little overview, Richard, about what is going to be addressed in the first assignment?
Yeah, for sure. So we're really going to focus on structured cabling in the first assignment. And basically what this comes down to is data is transmitted in bits. So it's either on or off, essentially. Digital data is transmitted by bits, but there's a variety of mediums that can be transferred over. For example, if you transmit data electrically, then you would need some kind of a wire, copper wire. That's
Okay.
typical. You have some sort of a jack you plug into. Well, all of those are standards as far as the length of the wire before attenuation starts to cause signal loss. You have standards as far as the jack types. You may have heard like RJ45.
Okay.
Those are standards for specific kinds of jacks. You might also transmit the data using light waves. So for example, fiber optic cabling.
okay. Yes.
And in fiber optic cabling, lasers are lighting up the cable, and they're basically being used to communicate with receivers on the other side that are then able to translate those light waves into, again, bits of data. So everything comes down to that fundamental, but there's a lot of choices when it comes to cabling. You can even transmit bits of data wirelessly. That's how your cellular phone works. That's how your wireless laptop works. This course isn't going to focus on that. We're focused on the wired aspect. But there is another course offered through SEDPA K-12, the TAPS organization, that focuses on microwave communication and all forms of wireless communication. But for this course, we're really focused on how data is transmitted over fiber optic and electrical circuits. And one of the things that you're going to learn is that there's limitations. And oftentimes the reason you choose one cable over another is because of those limitations.
Okay.
There's distance limits, there's bandwidth limits, there's other things that are inherent to
And I
the
imagine
cable you choose.
one might work better than another in different situations. or-
Yeah, as a broad example, when you're connecting two buildings together, you oftentimes are going to go fiber optic. And you'll see why as we go through the assignments. But basically, it really comes down to distance and also the fact that fiber optics are pretty difficult to affect with water.
Oh, well,
It's a strand of glass, you know? So it's pretty impervious when you bury it in the ground. It does a pretty decent job of staying in service for a long time.
Okay.
Whereas copper, if any water gets through the outer sheathing, it could rot or it could, corrode, obviously. And also copper cabling just has distance limitations that are much, much shorter than fiber optic cabling.
But when would you use copper then over fiber optic?
Well, once you're inside of a building, the distances aren't that great.
Okay.
You basically have the distance from the communications closet to the user's desktop.
Okay.
And that distance, as long as it's under about 300 feet or 100 meters, then it's acceptable for modern copper cabling, even up to high speeds. So we've even gone beyond 1 gig. We're now looking at 10 gig copper cabling. And it's acceptable to do that as long as you're within those distance limitations.
So if you were going to describe a typical K-12 network, what kind of cabling systems, or how are those usually laid out in terms of fiber optic versus copper versus other things?
Sure. So as far as what kind first, you typically would go with category 6 copper cabling within the building, and that's going to be used to basically energize. So you're going to have some sort of power over Ethernet, so you're going to send power to power up access points or maybe VoIP handsets, things like that. Copper cabling.
Voice over IP.
Voice over
right?
IP, right,
Okay.
right. And copper cabling is excellent for that because on that copper cable, you can transmit data, but you can also send power.
Okay.
And it's very useful for that in a modern K-12 environment. So the access points don't have to have individual outlets, but instead they're powered from the switch, basically.
Oh, that makes a lot of sense.
It's incredibly more efficient.
You don't have to have a plug next
Right,
to
or
everything.
hire an electrician
Right.
to run an outlet in the ceiling, for this
Right.
access point. Instead, you just have to have the low voltage cabling going back to the switch. So typically, you're going to see just a lot of Cat 6 cabling. Same thing with wired smart boards. It's going to be typically Cat 6 cabling. And then from the buildings, you're typically going to see multi-mode fiber until the distances get up over about 1,000 feet, and then you'll start to see single-mode fiber. We do dive into the differences, but in a broad way, multi-mode is a wider wavelength, and single-mode is a narrower wavelength. And the narrower the wavelength in fiber optics, the longer you can transmit into the kilometers.
Oh,
so with
wow.
single-mode wiring, that's the kind of cabling that like a telco would use in order to communicate over long distances, even across the Atlantic Ocean. They have repeaters, but that's typically single mode fiber optics to get that kind of long distance communication.
Great. So that sounds pretty exciting. So the
I
first
hope so.
assignment is all about cabling.
It's all about cabling.
Yay. Hi everybody, I'm Kathy Resnicek.
I'm Richard Pressler with All Connected.
And today we're going to be talking about assignment 2 in module 1 in the networking fundamentals module.
That's right.
In the Tapped Wired program. Whew, that's a mouthful. All right.
The title's almost long enough to make the whole course.
It's great though. So assignment 2 is looking at all the equipment that goes in a wired networking network, right?
Right.
So we talked about all the cabling that we need to kind of hook everything up in assignment 1. So give me a little bit of overview of what we're going to be seeing in assignment 2.
Sure. So now we're talking about what to plug the cables into, because cables on their own are useless, right?
Well,
they don't do anything.
Cat toys, but other than that. Yeah.
So now we're going to get into what is a hub, what is a switch, what is a router,
Okay.
what is a firewall. These are basics that are necessary in order to understand how all of these components fit together.
That makes
And some
sense.
of these pieces of equipment are quite expensive too, so it's important to really understand what they're capable of. Now, when you're picking a switch, for example, oftentimes you're picking it based upon the medium available. So if you have a lot of Cat6 cabling, then you're going to need switches that have a lot of ports in order to support all of that cabling that has been installed. So sometimes you'll even see in a closet, you'll see stacks of switches on top of each other to provide the port density necessary. And then from those switches, you'll often have some sort of a backbone. It could be fiber optic, for example, which we talked about in assignment 1. But you'll have a backbone that connects that closet to, say, a master closet, a main distribution frame, or MDF. So you could have a distribution.
I always wondered what that MDF stood for. That's great.
Well, you have intermediate distribution
Yeah.
frames, which are the small closets where switches go to support
IDFs.
end users, IDFs, and then you'll have MDFs where all the aggregation occurs.
Okay.
So you basically will have these different types of connectors. You might have fiber optic transceivers, for example, and so the switch has to support those various types of connectors.
That makes sense.
Something that's critical to understand for this assignment, Kathy, is that it's all about segmentation, really. When you dig into the types of equipment, they are providing various levels of segmentation within the network. So for example, a hub really doesn't provide any segmentation. A hub, and that's why we don't use them much anymore, everybody plugged into the hub has to figure out when they're allowed to talk and when they have to listen with each other. So there's a lot of errors. There's a lot of collisions
Right.
where two computers are talking at the same time on a hub, and therefore that data is essentially corrupt.
So who can go and who has to wait?
Yeah,
Start and
almost
stop,
like getting onto the freeway,
Yeah,
right?
right.
With no light system. Like
Yeah.
you just have to work it out with the other drivers. And the more lanes there are to get on,
Yes.
the more chaotic it becomes. So we don't use those much anymore.
Okay.
But we use switches, and switches provide collision domain segmentation. So on every single switch port, it's essentially a collision domain. So you have
Okay.
your own private lane onto the freeway, you could say.
Oh, that's nice.
You have your own access when you're on that switch port. And then routers provide logical segmentation between entire networks. So a router will be the segmentation point between say an IP subnet.
Okay.
So your entire addressing segment will exist in one interface of the router, and then it's responsible for getting data to the other segments. Or say on the internet, it's responsible for getting data to other routers to transmit across the internet.
Which is really important.
Yeah, and we use the internet a lot because everyone understands somewhat
Right.
like how it works, but
Yeah.
really it's just a massive WAN. It's a massive network
And
of
a WAN
routers.
is a
Wide area network.
Okay.
Yeah, and the internet's the widest area network, you could
widest,
say. Well, at
yes.
least until there's interplanetary communications.
well, yeah.
But the equipment we're talking about here is really it's segmentation.
Okay.
One thing you'll notice in this assignment is that some equipment has overlap with features with other types of equipment. So for example, you might buy a switch that also has routing features. So that switch could act as a router on your network, and it
Okay.
could do that IP segmentation, right? You could also buy a firewall, and the firewall seems to have a lot of routing features. It supports routing protocols, it can route between segments, and that's all true. But for this assignment, don't get mired down in those kinds of details too much. It's important to focus on the reason that the piece of equipment exists in the first place, and try to gain an understanding of what it's doing at layer 1, what it's doing at layer 2, what it's doing at layer 3 of the model we're going to talk about at the end of the course. But basically understanding where is its segmentation.
And so that's really interesting, but it sounds like there's a lot of equipment to consider, and it kind of sounds expensive. So how do most K-12 districts who, most of us struggle with finances just to keep a good school afloat or to keep our district office running? So how do you deal with all this equipment and budgetary issues?
Well, one thing I think that really helps K-12 school districts is to realize the purpose of the piece of equipment and not get too stuck on the manufacturer. That helps reduce costs because then when you're putting out a bid, for example, in the bid you can say this equipment has to do X, Y, and Z because it's a switch and we need it to be a managed switch, for example. We need it to have these features. But you can get the manufacturers to kind of bid against each other and give you better pricing because you're not locked into a single manufacturer. And what's nice is we're almost in all cases talking about standards-based protocols. So everything we're discussing is compatible from one switch manufacturer to another switch manufacturer. So you can plug a fiber optic cable from an HP switch into a Cisco switch. And you're not really worried about whether or not it'll function as long as you understand the wavelength that fiber optic transceiver is operating at and that they're fundamentally compatible with each other. Well, once you have that knowledge, you can save the district a lot of money just by understanding what the equipment is really capable of and using it to its maximum efficiency, basically. And I'm hoping that this course helps people to realize that and to kind of understand the equipment choices that they're making. And some of it is very expensive. You can't avoid that at all times.
But you
should
want to
know what you're getting.
maximize what you can get.
And purchase what the district needs, not over purchase, right?
Well, that makes a lot of sense. And speaking of bidding, in the TAPT program, we also have a course on procurement.
Oh, that's right.
And that's where you can learn all about the bid process, the RFP process, and all the exceptions there are to all of those components. So,
There you go. Excellent.
Hi, everybody. I'm Kathy Resnicek.
And I'm Richard Pressler.
And we're here to talk about Assignment 3 in the Network Fundamentals module in the TAPT Wired Networking program.
Excellent.
So we talked about cables, we talked about equipment. So what are we going to tackle in Assignment 3?
So now we're going to talk about the rooms the equipment goes into. We talked a little bit about the expense of this equipment, but I really want to focus in on that. Some of these pieces of equipment are worth thousands of dollars when they're procured, and it's important to make sure that they get the maximum lifespan. Well, the manufacturer kind of dictates how much airflow they expect, how much dust they expect, and it's up to us when we're designing a room that it's going to go in to make sure that it fits within those manufacturer specifications. We're going to be talking about a guideline called ASHRAE, which is basically a center that dictates how data centers manage their temperature and things like that. They provide a set of guidelines that are good for people to understand, even if they can't always comply with them. One of the challenges in K-12 school districts is that the equipment room is often chosen for you. So you may find that you're left with a electrical closet. Yeah, exactly. In one case, I had a high school where the equipment room that was chosen for the gym was actually the gymnasium storage room, where all of the equipment had to go. And so when we went in to service the equipment, we had to wade through all of this paraphernalia and gear and pull it out.
Basketballs and soccer balls. And,
it wasn't a great idea. And also, if you think about who has keys to that room, it can be a variety of people, and maybe they shouldn't. So we're going to talk a little bit about physical access in choosing a room. We're also going to talk about how the room selection affects cable distances. So in Assignment 1, we talked a lot about cable distances, and hopefully the magic number you took away from that assignment was 100 meters, because that's about as far as you can go with Cat 6 cable.
That one's on the test.
Right, that one's on the pop quiz.
All right, there we go, got it.
But that does mean that you would not want an equipment room for a floor of a building to be farther than 100 meters as the cable runs from the network drop that it's going to be located at, right? So oftentimes that indicates that the equipment room should probably be kind of in the center of the building. That's a logical place to put it. And so we'll talk about that a little bit in this assignment. We'll look at some of those guidelines and recommendations. But the overall message to get through is that the equipment is expensive, it's worth protecting, it's worth keeping it both secure and keeping airflow to it so that basically it has the maximum lifespan it can possibly have.
Well, I imagine if you're building a new school, you know, you can take all that stuff into consideration. But, you know, I know that some of our school buildings have been around for a long time. There's even a couple of our school buildings that still have fireplaces in the corner from when they didn't have central heat.
Wow.
So I imagine you have seen some pretty interesting equipment setups besides the gym room.
Oh yeah, yeah. I mean, for quite a while we were putting little racks on the wall in the classroom. And the problem with that is that some of this equipment, it has very high-speed small fans. And so it would actually disrupt learning just because the equipment would sound like a little jet engine taking off as it powers up. And of course, in some cases, we can buy fanless equipment, things like that. A fanless switch, for example, to keep that from happening. But it does, you have to work within those constraints. And putting that rack on the wall is just not ideal. You know, it's kind of an eyesore, the noise issue, it's hard to secure. But it worked. And it got us through, you know, that time period. Sometimes with an older building, it's possible to look at the building plans and realize that there is a more logical place to put the room. You know, you're not always forced to put it. We don't really have computer labs as much as we did. That often forced a decision. When we had computer labs and you had, say, 40 or 50 computers in one room, well, you oftentimes would put the equipment close to that lab. But now we're much more distributed, I find. So maybe there is a place in the building that's more logical. But sure, I've seen nightmares. Somebody put it in a women's restroom once for me, and I had all male employees at the time, and so it was very difficult for me to like shut down the restroom in order to get to this switch up in the wall. And I think that one was also about 12 feet off the floor.
Oh wow!
So it was up in the ceiling area. Yeah. So you do see some strange installations. But rather than me talk about just horror stories, we're going to focus in this assignment on what's right. What's the right way to do it? And that way you can go to a room and look at it, even your equipment room right now. You could go check it out, take pictures of it, and say, well, does this comply with the standards? Is this really going to maximize the lifespan of the equipment? And there's other factors too. For example, in the state of California where we are, racks need to be secured in case of an earthquake. So you don't just have a freestanding rack like on wheels with equipment in it. In an earthquake, that would be a nightmare. So it's important that things are properly bolted to the floor, anchored to the wall, and secured in a way that they're going to minimize damage in the event of an earthquake.
That makes a lot of sense. Well, that's going to be really fun, exploring how do we take all this equipment and set it up right.
Yeah, keep it alive as long as we can, right?
Awesome. Great. Thanks.
You're welcome.
Hey everybody, I'm Kathy Resnichek.
And I'm Richard Pressler.
And we are going to be covering the final assignment in Module 1, which is in Network Fundamentals and the Tapped Wired Networking Program. So last but not least, what's the exciting conclusion to this module?
Well, now we've done the lab work, you could say. We've done the hands-on work that we were able to do by looking at the physical aspects of a computer network. And now we're going to talk about a model. And what a model is, when we use that word in this context, we're talking about something theoretical, something that you could basically draw out, but it describes a network in very broad terms. Now there's several different models that you can review to understand computer networks. The one we chose is the OSI model, the Open Systems Inter-Network model. And the reason that I chose that model to discuss is because it's broad enough to cover all other models. It's broad enough to cover any protocol at any layer, basically.
So it's the mother of all models.
Yeah, and some people feel it's kind of clumsy because it is actually a little bit too large, and I'll dig into that a little bit for you. But essentially it divides a computer network up into 7 layers, and those layers essentially dictate how programs or applications at the top would communicate all the way down to the cabling at the bottom, or wireless communication. Somehow the bits have to get from point A to point B. So as an example, let's say you have an email client, and that email client is going to communicate with an email server. Well, the email client has to speak the same language as the server in order to collect the emails, right?
Right, that would make sense.
And speaking the same language actually goes even deeper than just how do I send an email. It goes into the TCP layer, it goes into the IP layer.
And
These
are you
all
going to explain
protocols.
all those, what TCP and IP and all that stuff
We get
is?
a little bit here, and then we get a lot in Module 2.
Okay.
Module 2
Looking forward
is
to it.
really deep
All right.
into all of those
Awesome.
protocols.
Okay, great.
But this gives a framework to understand where those protocols even fit.
Okay.
It also gives a good framework to understand where equipment fits.
Mm-hmm.
So for example, when we say a switch, well, once you've read through this model and understand it, you'll say, well, a switch is generally operating at layer 2 of the
Okay.
model. When you say I have a patch cord, a cable, that would be considered layer 1 of the model. A router would essentially operate at layer 3 of the model.
Okay.
Now, when we get above layer 3 is when it gets kind of tricky, because some people would claim that once you get past layer 4, which is session reliability, it's the ability to guarantee that two parties are communicating with each
Okay.
other and actually receiving the data.
That's important.
But once you get beyond that, you are getting into applications. And that's really the territory of programmers for the most part.
Okay.
So layers 5 through 7 are considered to be things that you need to understand when you're developing applications that are going to speak on a computer network. So we're not going to spend a lot of time on that because most network equipment doesn't really look at layers 5 through 7 other than some very expensive, very nice next generation firewalls and some routers that have the ability to identify applications.
Okay.
Beyond that, for the most part, network equipment looks at layers 1 through 4.
Okay.
And that's where we're going to spend a lot of our time.
Great. That sounds really good. So you talked a little bit about the different layers, and so for someone who is responsible for the network, the understanding the OSI model really gives them that understanding of where each piece of that network sits in those 4 layers. Is that right?
Yeah, it's a way to contextualize things and
Okay.
to organize it,
Okay.
really is what it is. So let's say, for example, that you're reading a paper and that paper is talking about some new protocol that someone created that works within an IP network, right? And perhaps this is a protocol that's designed to help phone handsets communicate with each other better, that maybe somebody came up with something. Well, if you have an understanding of the OSI framework, what that does for you is it helps you just kind of plug that new piece of information into where it sits in the entire
okay.
stack so that you understand what goes under it and what goes above it.
Yeah.
As you've learned up to this point, you can't really have a wired computer network without wires or
Right.
fiber optic cabling. You can't really have a wired computer network without switches and routers. Well, when you talk about protocols, you also can't really have a wired computer network without protocols because people have to be able to talk to, or computers have to be able to talk to each other,
Right.
I should say.
Well, people
too,
but
but
we don't have those protocols in place so much as we do for computers. But
Well, there you go. And so when two computers are speaking to each other, it's important that the developers who basically wrote those protocols for those computers were on the same exact page and that they can communicate in the same language.
Yep.
And so understanding this model helps you to understand where that's possible and where it may not be possible.
it sounds really interesting.
I hope it is.
And I think it's a great way to wrap up this module because it kind of ties all those fundamental pieces that we looked at earlier, and it puts the theory behind the practice.
Yes, that's my hope.
Okay, great. Hey everybody, I'm Kathy Resnicek,
I'm Richard Pressler with All Connected.
and we're here to introduce you to Module 2 of the Wired Networking course offered by TAP. So in Module 2, we're going to look at the LAN and WAN protocol. So can you tell us what we're going to be experiencing in this module?
Absolutely. So essentially, there are standards that have been agreed upon in order for computers to communicate with one another. And understanding those standards is very helpful because ultimately you may be called upon to troubleshoot a problem between computers that aren't talking to each other, for example, and you need to understand why, right?
So when you talk about standards, is standards and protocols, are those the same?
They're kind of
thing, or-
interchangeable.
okay.
Think of it like a diplomatic protocol, right?
Okay.
So when countries meet together, there's protocols about who can talk to who. There's protocols about maybe even the language that they use. They may need to agree on the translators and things like that. So humans often do this. We often have some sort of standard or protocol for how
Okay.
we interact with each other, but we also understand context. So as a human, I can understand context clues in order to understand what somebody's talking about or how to deal with them, right? Well, computers don't really have context. They have no concept.
Not
so,
yet.
so when we say protocols in a computer, not yet. Yes, artificial intelligence may change that.
That's right.
But when we say a protocol in a computer context, we're really talking about a very strict standard,
Okay.
usually dictated by a document called an RFC, or request for comment. And that document will indicate exactly what problem a researcher or a programmer was attempting to solve and a solution to it. And if everyone adopts that, then they've adopted the same solution to the same problem.
Oh, okay.
So now computers can talk to each other. But they talk to each other at many different layers of the OSI model. So when we talked about the OSI model,
Right.
we talked about transmitting bits through cables at layer 1. Well, then it gets more complicated when you get to layer 2 because you have to agree on who are you talking to, what's their address, right? Well, that address has to have a standard. How long is it?
Okay.
How are they unique? How are they kept unique? So at layer 2, there's addressing. Also at layer 3, there's addressing. There's logical addressing in order to communicate with each other. So the assignments are broken up somewhat like that. The assignments are basically broken up into first the Ethernet standard, because that's definitely the
one.
most common layer 2 standard on the entire planet. Even your cell phone uses Ethernet. And then we'll talk about layer 2 non-Ethernet standards. Those are less common these days. In a K-12 district, you may hardly run into them at all.
Okay.
But it's important to understand that they're out there. And then we'll talk about layer 3 addressing protocols,
Okay.
specifically IP. That's the one that kind of won the internet.
The big one.
When the
yeah.
internet protocol became the de facto standard, then all of the corporate networks and K-12 networks essentially have adopted
Yeah.
that.
Yeah.
And so very few layer 3 protocols are really common outside of IP.
Okay.
That's it. But there's two types of IP. There's IP version 4 and IP version 6.
Oh,
And so we're going to
okay.
dive into why that is and what problems are solved in IP version 6. And today in America, I would say IP version 4 is just where we're at within the K-12 community, but we're working towards IPv6
And that's
rather
more
actively.
business or other countries?
It's just
or?
the internet. Well, other countries were forced to adopt IPv6 earlier,
Oh,
for
okay.
example, in Asia, because there wasn't enough IP version 4 address space on the
Ah.
internet to allocate to the country in order for them to use it. IPv6, on the other hand, has exponentially greater number of addresses
Okay.
that are available.
So we used up all the area codes first, and then
Kind
they
of.
had to get new ones. Okay.
Yeah, yeah, and area codes are only in a country. The
Right.
internet is everywhere.
Exactly.
So it's an even bigger
Yes,
problem.
yeah.
But it's also become a problem within some private enterprises and within school districts. So we'll talk about that.
Okay.
And then there's also other protocols that are necessary to exchange routing information
Okay.
between routers
Right.
about where a network lives. And so we're going to talk about a few of those, specifically RIP, OSPF, and BGP.
Okay.
And those are protocols that are used to determine where a network exists and therefore, and when I say network in this case, I mean like an IP segment, where it exists and therefore where to send the traffic to, what router to send the traffic to.
And you're
so
going to
those are
explain all
important
those
protocols.
acronyms in the assignments.
Oh
right?
yes, definitely.
Okay. So one last thing is the title of this is WAN and LAN protocols. So just for in case anybody doesn't know what a WAN, what does that stand for, and what does LAN stand for?
Sure. So WAN is a wide area network,
Okay.
and LAN is a local area network. You might also hear another term like MAN, Metro Area Network.
Oh, is that like a city?
Yeah, usually within a
Okay.
city. The interesting thing is that the protocols are often very similar. So it used to be that a WAN would use different layer 2 protocols than a LAN.
Oh, okay.
But now I'm finding new circuits from service providers are often Ethernet based. So therefore they're using the exact same layer 2 protocol that I use on the LAN.
Oh.
So the differentiation is becoming more difficult to really draw a line and say this is a LAN, this is a WAN. But for a school district, the way I would view it is the LAN is generally the pieces of the network you own, and the
Okay.
WAN is the things you have to connect to, like for a service provider.
Okay, that makes sense.
If you think of it that way,
Yeah.
that will provide a logical segmentation. It's not the only way to think of it, because some people would also say a LAN is the layer 2 segment and the WAN is when you're crossing layer 3 boundaries. But for the context of this assignment or this module, I would say look at it as the LAN is things that you have in your district, you own them, switches, everything. And then the WAN is things you're connecting to outside your district,
Okay.
like the internet, or maybe you had to lease a line from a provider to get 2 buildings to talk to each other. That would be like a WAN.
Great, that makes sense.
Does that make sense?
All right.
Okay, great.
Looking forward to it.
Let's get started.
Hi, everybody. I'm Kathy Resnicek,
I'm Richard Pressler.
and we're going to be looking at the first assignment in Module 2. And the first assignment looks at Layer 2 Ethernet protocols. So why do we need a whole assignment just on Layer 2 Ethernet protocols?
Because that protocol won, essentially. It became the de facto standard for nearly every type of communication that exists on the planet, really. At one time, there was different layer 2 protocols that were competing with each other. And oftentimes,
Betamax versus VCR?
VHS.
Okay, Blu-ray.
Kinda.
Let's go
Right,
Blu-ray,
right.
DVD.
We have to modernize our
I know.
analogies, right?
I know. Pong versus Space Invaders.
No, yeah, there are we've always seen fundamental incompatibilities in other industries, of course. But within the computer networking industry, manufacturers, they had engineers on staff who would develop protocols. And then within that manufacturer, the equipment could communicate with each other, and it could communicate with network cards that were manufactured by that same company, but they couldn't really communicate with anyone else.
Okay.
And that's the way the industry existed for some time. For example, HP developed a standard called 100 VG AnyLAN. And it was really a good standard. It was a 100 megabit per second standard. It used tokens, kind of like Token Ring. But basically, over time, it lost because it was proprietary to HP only. You would have to buy their equipment, their network cards. And Ethernet is the standard. It's the de facto standard. So when you buy a computer and it's got a little RJ45 cord on it, or port on it, that is essentially connected to an Ethernet chip. And when you buy a switch today, it's an Ethernet switch. There are not any non-Ethernet switches that you could acquire.
And Ethernet is open. It's not a particular company or product.
Yeah, essentially it's under a standards body, the IEEE.
Okay.
That body has decided that Ethernet, which is also called 802.3, but that is a standard that anyone can use.
Okay.
So chip manufacturers have developed chips around that standard, and then switch manufacturers have used those chips in order to build switches. And essentially, they've created an environment where, as a school district, you can buy a switch from any manufacturer, and you're almost guaranteed that it can just plug into a switch from another manufacturer and function. That's the beauty of having a standard. That's the beauty of having a
really
protocol.
helpful.
Oh, yeah. And within the Ethernet protocol, it addresses all the things that you need at layer 2. So essentially, it has the necessary ingredients for physical addressing. So there's a way to say that a chip has a specific, unique address.
Okay.
And therefore, when it communicates to another chip on the network, another computer on the network, they both have unique addresses so that there's not any possible overlap.
Right.
And then a switch is able to take those addresses and understand what port of the switch that they live on. So now it's able to forward traffic efficiently. It's not sending it out all ports, but rather it's sending it just from the source to the destination.
Nice.
And that's all dictated within the Ethernet standard, within
Okay.
that protocol.
Well, I can see why it's really important and that we want to have a whole assignment dedicated to that. So.
Yeah, definitely. And it's also a good foundation, because we're going to talk a lot about frames. We're going to talk
Okay.
a lot about protocol data units. So whenever we discuss a protocol, it usually has some way of creating a header and maybe a footer that encapsulates the data so that when it's sent out, the switch knows where it's going and maybe where it came from.
Oh, that's,
And
yeah.
so Ethernet is a good place to start for that because
Okay.
it's a pretty easy to understand header concept,
Okay.
and it's pretty easy to understand how the frame is built in its entirety. And so we'll dive into that, and that kind of gives a nice framework when we go to talk about non-Ethernet layer 2 protocols. We can always do it in the context of what we've already discussed for Ethernet.
And that's what we're going to be visiting in our next assignment.
Very good.
Hey everybody, I'm Kathy Resnicek,
And I'm Richard Pressler.
and we are going to be talking about assignment 2 in module 2. So the first assignment was Ethernet layer 2 Ethernet protocols. And so the second assignment is layer 2 non-Ethernet protocols. So what's the difference between the two, and does somebody really in K-12 need to understand the two differences?
Well, like I mentioned in the first assignment, Ethernet kind of won.
Yeah.
So it's the de facto standard. Just about everything speaks Ethernet. But there are some cases where Ethernet is not the best choice or is not offered. For example, if you order a circuit from a telco, that circuit
And a
could
telco
arrive.
would be something like,
Frontier Communications, AT&T,
Okay.
you know, you can still order circuits that are non-Ethernet based circuits. And so when that circuit arrives and you're plugging it into your equipment and starting to set it up, it helps to have some understanding about what is the protocol that's allowing communication. Because
Okay.
again, we go back to the fundamentals. We still have to get bits from point A
Right.
to point B.
Okay.
And we have to agree with how we're going to communicate at a higher level than just sending a bit. And so non-Ethernet layer 2 protocols exist for the purpose of dictating communication. They solve some interesting problems. For example, when we were studying Ethernet, you may have realized that a frame, an Ethernet frame, can be sent whether or not the receiver is ready to receive it.
okay,
So it can be sent with a MAC address as the destination, and the switch has to basically decide where to send it from there, but the sender had no real awareness of whether or not the receiver was there or was ready to receive that particular frame, right?
yeah,
But there's other ways of communicating, and essentially that's a way of defining a packet switched network. So in a packet switch network, a packet is dropped off on the network with enough addressing information to get from point A to point B,
Okay.
and the network can decide how to get it there based upon the address. In a circuit switched network, it's more that two entities have built a constant circuit to each other where they have synchronized that circuit so they're aware of whether or not the other party is ready to receive.
okay,
And it's kind of like a guaranteed way to make sure that no data is ever lost. It also is a way to secure your bandwidth, because now instead of everyone sharing a common pool of bandwidth with a bunch of
Right.
packets on it, you would have a dedicated circuit between two pieces of
Okay.
equipment. The analogy I would use is that it's kind of like having a fire hose. A fire hose does not deliver data or does not deliver water in bursts when it's working
Right.
properly, right?
Right.
Instead, the fireman, he opens the valve, and the fire hose really only functions when it's full. That's the only time it really
Right.
works, right?
right,
So it's completely full with water. Well, the same thing is true if two routers are using a circuit switched protocol. Well, they will establish that circuit to each other, and they will utilize all of the bandwidth allocated on that circuit, even if the router doesn't have anything to send. It'll just send garbage data in order to keep that pipe
full.
open. And by
Okay.
keeping it open, it knows that the receiving party is ready to receive that communication. This is very important when you're trying to conserve bandwidth. This is important not so much in a local network,
Right.
but on a wide area
Okay.
network where bandwidth can be expensive. It's important to understand that this is one of the solutions that engineers have come up with in order to allow two pieces of equipment to communicate with each other. It's not Ethernet at all,
Right.
but they agree on how exactly they're going to connect to each other, how the circuit's going to work, what the framing's going to be on the circuit, how their clocks are going to sync up. All of those things are dictated by these protocols. So I'll say they're less common.
Yeah.
You don't run into them as often in K-12, but it's good to understand how they work.
Oh, great. Well, that'll be an interesting little bit.
Yes, it will.
Great. Hi, everybody. I'm Kathy Resnick,
And I'm Richard Pressler.
and we're going to be talking about the third assignment in Module 2. And the third assignment looks at Layer 3 addressing protocols. So give us an insight into what the assignment's going to be about and what are people going to be learning in this section.
Sure. Well, as you can imagine, there's been different Layer 3 routing or addressing and routing protocols that have been created over time. But the one that essentially is the standard is Internet Protocol, IP.
Okay.
And so this assignment really focuses on IP version 4 with a little bit of IP version 6. The intention is that the student at least understands why we need to move to IP version 6, the advantages of it, some of the limitations of addressing that we have in IP version 4. But the most of the material is honestly on IP version 4 because that's what's running on most networks. It's what runs on the internet. That's what powers the internet. When you ping google.com, you get back basically 4 numbers separated by decimals.
Right.
Well, that is an IP address. And that IP address, understanding how it's built, how you assign them on the public internet, how you assign them on a private network, understanding how much space there is available within the IP ranges, understanding how subnetting works. We're also going to talk about classless interdomain routing, which is essentially a way of breaking IP subnet blocks up so that they can be smaller and smaller networks.
Okay.
We'll have a little bit on classful routing, which is the way the internet used to function back when you could actually look at someone's address and determine what size organization they were. Nowadays, you can't really do that anymore. The addresses have been mostly used up. So right now, on the internet at least, addresses are being assigned just as they become available. But it's good to understand a little bit of the history there, and then get into how the internet functions essentially, and how your modern computer network functions, because your computer right now no doubt has an IP address,
Right.
and it's communicating to a server that has an IP address, and somehow you're getting from point A to point B, and so we'll dig into how that works.
Yeah, because a lot of us just plug it in and it works, right?
Right, yeah, there's protocols like DHCP, which assign IP addresses to workstations. And that's important to understand how those protocols work, because when they break down, it might be your job to try to fix it and figure out what's really going on. So we'll talk a little bit about IP address dynamic assignment with DHCP in this assignment as well.
Great. Sounds excellent.
Good.
Hi, everybody. I'm Kathy Resnick,